Alright, in this lecture what I like to do is work through some examples from the end of chapter problems for chapter 6. I'm going to start with a couple of examples on relative motion. So let me see, let's tackle this simple problem here. Problem states that a boat takes 3 hours to travel 30 kilometers down the river, then 9.5 hours to return. How fast is the river flowing? So we have our river, and here is our boat, and the river, of course, is our moving reference frame. The boat, we assume that it has a motor that propels the boat forward in the river with some velocity v prime. This is with respect to the water. The water is, let's say, moving down river with velocity capital V, and for an observer who's standing on the river shore, the observer observes a velocity for the boat downriver, which is given by v prime plus v. This is the Galilean transformation function, as you know. And when the boat is traveling upriver, so here's the boat, and now the boat is traveling upriver, the velocity with respect to water is still v prime, but now the observer sees a velocity upriver which is minus v prime plus v. The plus capital V doesn't change in magnitude nor sign. That's the velocity of the moving reference frame, i.e. the velocity by which the river flows. But notice that v prime switches sign between going downriver and upriver, of course. So what we have for velocity downriver is 30 kilometers divided by 3 hours, simple math. And for velocity upriver we have 30 kilometers divided by 9.5 hours. So and if you then take a look at equations 1 and 2 and do 1 plus 2, you end up with 30 divided by 3 plus 30 divided by 9.5 on the left hand side is equal to 2v, from which you can figure out what v is, capital V is, which is the velocity, how fast the river is flowing, which is what the problem was after. Now let's take a look at, let me see where that is. There we go. We have Susan driving north at 40 miles an hour, and Sean is driving east at 35 miles per hour. They're approaching an intersection. What is Sean's speed relative to Susan's speed? Let's do a very quick pictorial representation. This is our intersection. We have Susan driving north. I've said that this is north, driving north, and her velocity can be written as 0I plus 40j. what I've said is that this is my east, north, south, west coordinate system. So this is my I unit vector and this is my J unit vector. And then I have Sean driving east at 35 miles an hour. So Sean's velocity can be written as 35 I plus 0j. So the relative velocity between Susan and Sean was simply V Sean minus V Susan, which is 35I plus 0j minus 0I plus 40j, which is equal to 35I minus 40j. So this is the relative velocity between Susan and Sean, or our capital V. So the relative velocity would look something like this. This would be the relative velocity vector between Sean and Susan, or in our free body diagram, actually it's not a free body, in our coordinate system, it would be something like this. Okay. Alright, let's take a look at some motion in two-dimensional motion problems. Here we have something that everyone has in his garage, a rocket-powered hockey puck. We're told that the rocket-powered hockey puck has a thrust force of 1 Newton, and we're given its mass. It is released from rest on a frictionless table 5 meters from the edge of a 2-meter drop. So here's our table, right? This is a 2-meter drop, and hockey puck is released from this position, which is 5 meters from the edge, and there is a thrust force acting on a hockey puck which has a mass of 1 kilogram. So when the hockey puck, while the hockey puck is moving towards the edge of the table, of course it's a linear motion. There is an acceleration in the x direction, which you can figure out by taking force in the x direction divided by mass, the force in the x direction in this case being simply 1 Newton, and the mass is 1 kilogram, so acceleration is 1 meters per second squared. Now the hockey puck reaches the edge of the table. It's going to assume a projectile motion. My mistake. It will not assume a projectile motion. In fact, it will still have the thrust force from the rocket. The thrust force from the rocket acting on it. So it will have an acceleration in the x direction, ax, but it will also have an acceleration in the y direction, which will be minus a g downwards. And if you do the analysis, you'll see that it will be a straight trajectory, because had it not been a straight line, had it been a parabolic trajectory, that would have meant that there was only acceleration along one direction acting on it, namely the y direction, the acceleration due to gravity. But we know that the rocket doesn't end its life when the puck is at the edge of the table. It in fact continues propelling the puck forward along the x direction. So what you need to do in such problems is figure out the velocity of the puck in this right here. So let's call this velocity 1x and velocity 1y, so whatever that may be, v1y. So this is the so-called launch velocity of our object at the edge of the table. Now vix, well, we know viy is 0, so v1y is 0 meters per second because the puck has no vertical velocity as soon as it is launched off the edge of the table. But as far as v1x, well, v1x you can figure out by saying that, well, we know v0x at this point is 0. It starts from rest, as I believe we're told that in the problem. And since you know your acceleration and you know the displacement here, which is 5 meters, you can use the kinematic equation to figure out what v1x is. Having figured out v1x, then if only you knew delta t, how long the puck is airborne, then it's a simple matter to figure out delta x right here, which is what the question is after. How far does the puck land from the base of the table? But how do we figure out delta t? We do not know delta t. So if you knew delta t, you simply multiply it by v1x to give you delta x. Actually, I made a mistake. You don't simply multiply it by v1x because I forgot that there is also acceleration in the x-axis acting on the puck. So if you knew delta t, then you can figure out delta x by saying that it's equal to v1x delta t plus 1/2 of acceleration in the x-axis times delta t squared. Okay, and this acceleration in the x-axis is our fx or m, what you had figured out in this section. Now, to figure out delta t, what you need to do is go ahead and analyze the motion in the y direction. So to find delta t, to plug into this equation, you need to analyze the motion along the y direction. To analyze the motion in the y direction, you know that use the kinematic equation again. Delta y, which is in this case negative 2 meters because we go from 2 meters down to 0. So our delta y is equal to minus v1y delta t. Now we know v1y is 0, so that's good. Plus 1/2 of ay delta t squared, and ay you know is a minus g, and since you know what delta y is, which is negative 2 meters, and you know minus g, so you can figure out what delta t is. Having figured out delta t, you plug it into this equation to give you delta x, which is what the problem is after. So as I had mentioned earlier, in this type of problems you typically analyze the motion either along the y or the x-axis to find what delta t is, and then you use that delta t in the other orthogonal axis to find things like velocity, displacement, etc. Another example is this skier Sam, who has a jet-powered skis, another object which we all have in our closets, I guess. So here the question is after how far does Sam land along the x-axis here, so we have the delta x, knowing that he becomes airborne, kind of follows a trajectory like this. and lands there. So you need to figure out what Sam's launch velocity is at the top of the cliff, which is 50 meters high. So you need to figure out what his v1x and v1y are. These are the launch velocities. And we also do know that there's an acceleration in both ax and ay, in both x and y directions, because he has a thrust force, a jet powered skis, so and also there's acceleration due to gravity acting. So if I were to do a free body diagram on Sam at this point, at the edge of the cliff, there is a thrust force which is acting at 10 degrees. This is the 10 degrees, and there's this weight acting like that. So using this free body diagram, figure out what ax and ay are, because you are given Sam's mass, of course. So use Newton's equation. Sum of the forces in either x or y direction is equal to mass times acceleration along either x or y direction. Once you know what the accelerations are, then you can use the kinematic equations just the same way that we used in the previous example to find delta t first, which is the time, the interval that he is the period over which he is airborne, and then use that delta t to find how far off the base of the cliff Sam lands, just the way we did for the hockey puck. Now, to find v1 and vx, you basically say that, okay, here I have v0 x and v0 y, and they're both 0. Sam starts at rest, and in this case I'm now going to say that for the first phase of the problem, my x direction is along the slope and my y direction is kind of it's just normal to it. Now, in fact, let me draw the y-axis at the origin. So this is my y-axis right there. So I know how far Sam moves up the cliff because I'm given the angle, and I am given the height of the cliff here. So I know the displacement along the x-axis while he is approaching the edge of the cliff. So using that, and v0 x as being 0, and ax, which is f divided by m, simply, then I can figure out what my initial velocity, or v1x and v1y are respectively at the edge of the cliff. So divvy up the problem into section 1 and section 2. You focus on your section 1, drawing your axes parallel to the motion, and once you figure out what the velocity components are at the edge of the cliff, then focus on the second part of the problem, where now your axes are, of course, have changed, but that's okay, because you can now forget about this section of the problem altogether. So long as you have the launch velocity information, the acceleration information, then you can work with your new coordinate system to figure out how far from the edge of the cliff Sam and lands. These problems are not difficult. They may be tedious, but they are not difficult. So if you follow through a systematic way and really try not to take too many shortcuts, you should be okay solving these problems. Here we have a sailboat traveling at some velocity. There's a sudden gust of wind that accelerates the boat, so just make sure that you draw your axes, and you indicate which way the acceleration vector. So here we have a acceleration vector acting on the sailboat. So this acceleration, from this acceleration vector, figure out what a east and a north are, or this is in other words what ax and ay are, and the velocity vector is given. The velocity vector is traveling east, so our velocity vector is like this. So that's our velocity vector. So remember that the x component of acceleration acts on the x component of velocity, and the y component of acceleration acts on the y component of the velocity. And the two equations that you use, of course, are velocity final in the x direction is velocity initial in the x direction plus acceleration in the x direction delta t, and velocity final in the y direction is velocity initial in the y direction plus acceleration in the y direction delta t. So what we learned in chapters 2 and 3, we apply the same things but twice. So really that's why I said these problems are no more difficult than what we've been doing so far. It's just that everything we've done in linear motion we repeat twice for a two-dimensional motion. Graphic analysis. We're given Vx versus time and Vy versus time for an object, and we are asked to find in which direction the puck is moving at 1 second. That's question A. If you notice that 1 second, you can read off what the puck's velocity is in the x direction and what the puck's velocity is in the y direction. And as I said, the direction that the puck moves, theta, is inverse tan of Vy over Vx. So a simple matter to find the answer to the first question. Now second question is, how far from the origin is the puck at 4 seconds? Let me change the color of my pen. At 4 seconds, these are the 4-second values. So what we need to look at is the area on the 0 to 4 seconds for Vx gives us delta x, how far the puck has moved along the x direction in 4 seconds, and the area under the curve of Vy over Vy versus time gives us delta y, how far the puck has moved in 4 seconds in the y direction. So having figured out delta x and delta y graphically, then you basically say that, well, the displacement of the puck, let's call that delta r, is square root of delta x squared plus delta y squared, using the Pythagorean theorem, of course. So it's very simple analysis here. I'll let you read this problem. What we are trying to do is we have a rocket that we launch, and there's a target that is moving in this direction with some velocity v, and we try to hit the target when the target is right above our launch area. So we try to hit the target right there. To do this analysis, we know what the thrust force is, so you can figure out what the acceleration in the y direction is, which is simply F over m. The rocket has mass m minus g, so don't forget minus g, because there's acceleration due to gravity acting on the rocket. And what we're trying to do is figure out exactly when we need to launch such that we hit the target when it's right above our launch position. So we are trying to figure out this delta x right there. But that delta x, the target is moving with constant velocity v, so that delta x is simply velocity of the target times delta t. What is that delta t? Delta t is the time that it takes for our target to reach this position, which is right above our launch site. But that delta t along the horizontal is the same delta t that's going to take our rocket to reach this vertical position. So the delta t's once again relate the motions in this case of two separate objects, one along the x direction, one along the y direction. Well, the delta t along the y direction, we know that we want to hit the target when it is 27 meters above our launch site. So we are given, so this is 27 meters. So 27 meters essentially is our delta y. So using the kinematic equation, delta y is equal to v naught y delta t plus 1/2 of ay delta t squared. V naught y is 0. We are launching our rocket. So delta y is your 27 meters. And ay is this term right here. So that's ay. So plugging all these into this equation that I have here, you can figure out what delta t is. So you can solve for delta t. Having figured out delta t, then go ahead and plug it here, because you know v is the velocity by which the target is moving, in this case 15 meters per second, and that will give you the answer that you're after, delta x. Rifle is aimed horizontally at the target 50 meters away. So let me do, it's my x-axis, it's my y-axis. There's the bullet, here's the target, it's aimed horizontally, and this here is 50 meters. Okay. And the bullet hits, well, the bullet's trajectory is a parabolic trajectory, it's a projectile motion, where ay is equal to minus g, and ax on the bullet, of course, is 0. There's no force acting on the bullet as soon as it leaves the gun. So, and this distance here, which we call delta y, is negative 2.6 centimeters. So that's my origin is 0, and this here is 2.6 centimeters below the aim point, i.e. delta y is minus 2.6 centimeters. So use the kinematic equation for displacement in the y direction to give you delta t, how long the bullet was in flight for, and then use that delta t and the 50 meter information that you have. 50 meters divided by time of flight is equal to your velocity in the x direction. And velocity in the x direction is constant, no acceleration, so you can figure out what the bullet's speed was when it left the barrel of the target, of the gun. Well, I'll leave you guys to work on this problem yourselves. This is once again, it's one of those problems that you analyze it in along the y direction. Actually, the ball is thrown horizontally 27 meters. Let me read this. So here's our x and the y directions, and the ball Thrown horizontally 27 meters per second, travels a horizontal distance of 54 meters hitting the ground. Alright, so the ball is thrown like this, and we're trying to figure out this delta y, and we are given delta x. So our launch velocity v0x is 27 meters per second, and v0y is 0 meters per second because the ball is thrown horizontally. Okay, so using the information that we have and the fact that ax is equal to 0, because as soon as the ball leaves one's hand there's no more any force acting on it, therefore ax is 0 in the x direction, but ay is equal to minus g. Alright, and here if we go with the ground being our 0 of the reference frame of the coordinate system, then delta y, the distance traveled, is well, you will end up with a negative value for delta y, so don't be alarmed, because the final position of the ball will be 0, and the initial position is what we're after, how high the ball was thrown. So use delta x is equal to v naught x delta t. V naught x is 27 and delta x is 54. To figure out delta t, I believe that's 2 seconds, and then use the delta t that you had, which is 2 seconds, I guess, 2 seconds, 54 divided by 27, and then use that value in the kinematic equation for the displacement along the y direction. Delta y is v naught y delta t minus 1/2 g delta t squared. Now this is 0 because v naught y is 0, so use the 2 seconds that you figured out here in this for delta t here, and now you can figure out what delta y is, and you will, as I said, you end up with a negative value because of this negative right there, but that's okay, that's exactly what we want, because the displacement as I've drawn it here will be negative. So whatever value you come up with, the height of the ball will be the modulus of the displacement in the vertical direction. I think that's enough problems as examples. I'm going to post similar problems for homework as well, so have fun.